So first, I want to point out something that might be misleading. There are fractions in the corner, and these numbers will not increase in the usual way, 1 out of 20, 2 out of 20. They will seem to go all over the place. And that's because when I left the US, I didn't bring the LaTeX source for 3 talks that I was going to pull things from. So instead I grabbed individual slides from different PDF files and put them all together. And so, you know, it'll say like American Math Society conference at some point. It will, so don't think that you're kind of having some drug flashback or something. It's just yeah, everything will change at the bottom. Just ignore the bottom. That's the only thing I want to mention. Okay, so this talk is about Matroid optimization. I'm going to assume that most people don't know about matroids, and I won't assume much about optimization, just that you know what it means to find the best of something. So hopefully I won't assume too much, and we have a common ground here. Matroids. Matroids were originally described by Whitney, who was a topologist, as a means of abstracting linear independence in vector spaces, of points in finite vector spaces. And he saw, you know, common properties of points in space and edges of a graph, really, and invented matroid theory and wrote this paper that gives many different axiomatizations of matroids. And other people were doing similar things at the same time, and it was just kind of a little mathematical exercise. And then the subject kind of went down for a while, and then it came back when Tutt really invented the subject of matroid representation theory, which is really a much more involved topic. And this topic still is very active today among a small number of people who are doing some very exciting work.
What does it mean?
Matroid representation theory. So I have to say what a matroid is, but if you roughly know what a matroid is, what you try to analyze is given a matroid described in a certain way, there's different ways the matroids come, I'll mention this in a second, what matrices over what fields can the same matroid arise. So for example, if a matroid can be represented over the binary field and over the real field, it can be represented over every field, and questions like that. So that's a whole other subject that has its own independent life. And what I'm going to be talking about is nothing to do with that really at all. It's algorithmic questions defined with regard to matroids. And there's very little in common of these two topics. Just the basic structures that you look at are the same, but they borrow really almost nothing from each other. This is backwards, and I have to remember that. So let me just briefly say what a matroid is. There's a finite set called the ground set of the matroid. You can think like the edges of a graph or points in space. And you decide that certain of the subsets of that finite set are called independent. And they should satisfy 2 very simple properties. One is that subsets of independent sets should be independent. And the other property is that if I have 2 independent sets, one bigger than the other, I should always be able to take an element from the bigger set that's not in the smaller, put it in the smaller, and get a bigger independent set, this exchange property. These are the 2 very simple properties. And you can see for linear independence, so if I had a finite set of points in some vector space, and I define independent sets to be the linearly independent sets, then they obviously have these simple properties. The other big example, motivating example, is graphs. If I define the independent sets of edges of a graph to be the acyclic sets of edges, then it takes a little bit to see why the second property holds, but it holds for that as well. I'm going to make this, it's not only that I'm left and right, but I keep wanting to press these top ones. So there are a lot of examples, And it's important to decide if you want to talk about algorithms for matroids, you have to decide how you're given the matroid. And so in the weakest possible way to be given a matroid is you just assume you have a black box. And the black box, if I give it a set, it returns whether that set is independent or not. And I don't know anything more about the structure of the matroid. I could discern some of the structure if I keep querying this black box, but generally speaking, the algorithms that would just use a matroid given that way wouldn't really discern much of the structure from a matroid that way. Then very simple examples are uniform matroids. So you have an n-element set and subsets of size r or less are independent. Then direct sums of uniform matroids. Direct sums of any matroids are matroids. So you have disjoint ground sets, matroids on these separate sets, and you just take the direct sum. These seem like trivial examples, but these partition matroids are actually rather important in applications. I mentioned these graphic matroids that come from finite graphs where the independent sets are the acyclic sets or the so-called forests of the graph. Linear independence. A really interesting example for mathematicians is algebraic independence. So you have maybe I won't even say what that is because most people probably don't care, but you can talk about whether numbers are algebraically independent, and this is a really interesting example. Then you get more matroids by duality. So there's a really nice duality principle. And then there's an idea of matroid union, which is I could have several matroids on the same ground set and say k of them. And I say a set is independent if I can partition it into independent sets in the k separate matroids. So for example, I could take the graphic matroid twice on the same ground set. And a set is independent if I can partition it into two acyclic sets. That sounds like a weird, maybe artificial construction, but there's actually interesting examples in statics of deciding whether a bar and joint network is rigid or not. Uses exactly that construction of looking at two graphic matroids on the same ground set. So using these kind of, these last two sorts of operations, you can take some of these more basic matroids and build more complicated ones. And some of these have applications, others are just interesting, from a theoretical point of view. So what's going on the algorithmic side? Well, very early on, maybe not Whitney, but around the same time, Rado realized that the greedy algorithm solves a certain optimization problem on matroids. So the problem is, let me just say it on a graph first. The problem on a graph is I have a finite graph, and I have weights on the edges, and I want it's a connected graph, and I want to find a maximum weight spanning tree. And an algorithm that finds that is the greedy algorithm. It's you take the biggest weight edge, and then you keep that, you never release it. And then you take the next biggest weight edge and you throw that into your set. And you keep doing that in order from biggest weight to smallest weight. But if taking an edge creates a cycle in what you already have, then you throw that edge away and never look at it again. And you just go through the edges in this order from biggest to smallest, always throwing in edges if they don't create a cycle with what you already have. And it's a very basic theorem in matroid algorithmics that works, that gives you a maximum weight spanning tree in a graph, and the exact same algorithm works for any matroid. Finds a maximum weight independent set in any matroid. What's less well known is that there's another algorithm that also does the same thing. You start with any spanning tree, and you think about an edge in the tree and an edge out of the tree, and if interchanging them keeps what was a spanning tree still a spanning tree, and if it increases the weight, you take that move. So you keep doing pairwise interchanges if they keep feasibility of the tree and make the weight go up. And if you do that until you can't do it anymore, that also gives you a maximum weight spanning tree, and it also works for any matroid, finds a maximum weight independent set. So that's all nice. What's deeper is matroid intersection. So again, if I have two matroids on the same ground set, and now I want to set, it's not the partition example I mentioned before. What I want to do now is say a set is a good set if it's independent in both matroids. Right? I have two matroids on the same ground set. A set is good if it's independent in both. So that's called a matroid intersection. And finding a maximum weight set that's independent in two matroids is a more complicated algorithm. It's not based on just the greedy algorithm. This problem generalizes finding a maximum weight matching in a bipartite graph. So a way to think about it is I've got a bipartite graph. So I've got a set of vertices here and a set of vertices here and some edges that cross. And I define two matroids on the set of edges. The first matroid, I stare at the left side of this picture, and I say a set is independent if there's no more than one edge touching any vertex on the left. That's exactly a direct sum of uniform matroids, where each uniform matroid just involves the edges that touch a single vertex, and I'm only allowed to pick one. So it's this matroid U1n. If there are n vertices touching, n edges touching that point, I'm allowed to pick at most one of them. And if I take the direct sum of these matroids for all these vertices, that's one matroid. Then I do the same thing on the other side. And a set that's independent now is a matching in this bipartite graph. It's a set of edges that doesn't touch any vertex more than once. And if you know some graph algorithmics, you know that finding a maximum weight matching in a bipartite graph, you don't do it by the greedy algorithm. There's really simple examples like that graph that tell you that the greedy algorithm wouldn't work. That if you have weights of 1 on all these edges and you pick this edge first, you're stuck. You can't pick anything else when you should have picked those two. So the greedy algorithm doesn't work for finding a maximum weight matching in a bipartite graph. It doesn't work for finding a maximum weight matching for two matroids in general because of that. So it's a more complicated algorithm. It's a very basic algorithm, but it's a much more complicated algorithm. So these are well-known problems and algorithms in Matroid optimization that are kind of classical, that date back. The first one dates back to, in some sense, to the 1930s, in another sense, even further back. If you look at, for spanning trees, so the first algorithm was by, I think, a Czech electrical engineer named Borůvka. And if you look at his proof, it works just as well for matroids, and you could think of it as almost defining matroids when he wrote that proof down. The algorithm for matroid intersection is by Jack Edmonds, that dates back to the 1970s. So these are kind of classical problems and algorithms in Matroid optimization. Then there's nice geometry associated with this. So for Matroid, you associate with a polytope. And the way you do that is you, for every independent set, well, first you have a component, you look in space of a component for every element of the ground set. And then you associate an independent set with a 0, 1 vector, where the ones pick out the elements in the set. And if you take the convex hull of the 0, 1 vectors associated with all the independent sets, that's a certain polytope. And the way I describe that polytope is by an inner description. I said take the convex hull of these points. But there's an outer description via linear inequalities, and it's exactly what I have there. That you look at any subset of the ground set, and you add up the variables that are indexed by that set. And you say that should be less than or equal to the rank of that set. The rank of the set is the size of a largest independent subset of that set. And if you write down all those inequalities plus non-negativity, that exactly describes the convex hull of the 0, 1 vectors of independent sets of Matroid. And what's really beautiful, and was also discovered by Jack Edmonds, is that if you take two of these matroid polytopes on the same ground set and intersect them, they have this lovely property that you don't need any more inequalities than the sets of inequalities from the individual matroids. So the convex hull of the sets that are independent in both matroids is described by exactly the inequalities for the individual matroids. And it doesn't work after that. So 3 matroids is not true anymore. So there's something very special going on for 2 matroids. And it's related to why there's a nice algorithm. So I'm going to talk about 3, probably 2, but ambitiously 3 pieces of work that try to extend this to make more complicated optimization problems defined on matroids and contribute something to their solution. So let me just describe very quickly, and then I'll get into probably the details just of the first 2. So the first one is what we call parametric nonlinear discrete optimization. And here's the general idea. I'm going to think of points x that are the 0, 1 vectors that are independent in a matroid or maybe even in 2 matroids. And instead of trying to optimize a linear function, I'm going to try to optimize an arbitrary function of a matrix W times those vectors. Now, why is there a W here? If I had the identity matrix, I would just say an arbitrary function of those 0, 1 vectors. So the point is that the shape of W is going to play a role. So I'm going to think about W's that have a very small number of rows, a constant number of rows, relative to, and what's changing is the number of variables. So I'm going to talk about that some. Then I'm going to talk about submodular maximization. So I'll say exactly what a submodular function is when I get to it. But this is optimizing a different kind of function than a linear function, where I have constraints of the same sort, that I should be independent in several matroids. And then this last topic that I probably won't get to, maybe I won't say anything about it at the moment. So that's the program, to try to come up with more involved problems than these 2 simple ones for matroid optimization. There's some stories you can tell about these problems, you know, in the classic sense of making up stories to write grant proposals and that kind of thing. But really, these were mostly defined as by trying to generalize, just for the sheer, fun of that, for the mathematical and computer science fun of generalizing, and really are not motivated by applications. But let's just keep that between us. Okay, so let's talk about the first one. The first one doesn't really have to do with matroids. It has to do with problems where I have this idea of reduced dimension. I've got feasible points. I'm going to multiply them by a matrix that has a small number of rows, and then I have an arbitrary function that I'm trying to optimize over this low-dimensional set. So the domain of f is small compared to the number of elements in the ground set. And you can think of this as a kind of paradigm for multi-objective optimization, where each row of W is defining a linear function, and f is somehow balancing those linear functions. So think of maybe f could be like the 2 norm, and maybe I have 3 linear functions that are described by the rows of W, and I'm trying to minimize the 2 norm of these 3 different objective functions. So the sets, how this relates to matroid optimization, you could think of f is the sets of 0, 1 vectors that correspond to sets that are independent in 2 matroids. That would be an example. But it really applies in a more general sense that I'll try to clarify in a minute. I should say a bit more. So somehow I think this was really a Keist slide. So I did do some latexing to get this thing ready. So the goal here is to get positive complexity results. So to say in polynomial time we can do something. And the levers are what the set of feasible points is, how the matrix W looks, does it have a small number of rows? In fact, the entries in W, how they're delivered to you, plays a role. And then what kinds of functions little f we're looking at. So there's several levers here. And the idea is to play with these levers and see what you can do efficiently and what you can't do efficiently. Let me just briefly say, I'm not going to read through this slide, that in general this is intractable. And there's lots of ways to see it, but let's think about this very simple case. If I make my W matrix look like a vector like this, and say every 0, 1 vector is feasible, that's a matroid. If every 0, 1 vector is feasible, that's the free matroid. Then if I think of W, this vector, times any 0, 1 vector, what I'm going to do is produce every possible number, right? In a range up to 2 to the n, or 2 to the n minus 1. So if I can produce every possible number, so the domain of little f, the effective domain, is every possible number from 1 to 2 to the n. And if f is arbitrary, the function, then the only way I can see whether I've optimized is to check the value of little f on every feasible point, and there's an exponential number of feasible points. So this is a provably exponential problem, just it's trivially exponential because there's too many points to check if I don't assume anything about little f. So there's another example there that shows it's intractable. There's another point here of what's intractable. That's if you give me an image of a point, a feasible point, I don't tell you x, but I tell you its image under W. And I ask you, this is a so-called fiber problem, I ask you, find me a point x in calligraphic f so that wx equals u, that's an intractable problem. So just even if I know where f should be evaluated to get me the optimal solution, recovering that optimal solution is not easy. So that's all the point of the slide is to say we've got to make some assumptions or this is just provably difficult. So here's the assumption we make. What we're going to assume is that the set of feasible points is well described. And what I mean by that is that in polynomial time, I can solve a linear optimization problem over that set. So for example, the independent sets in a matroid, or the independent sets in two matroids. I can optimize linear objective functions over those sets. So my assumption is that I can solve linear objective problems efficiently. And now I want to solve these, f of wx problems. Now you shouldn't be looking at optimizing that kind of objective function if you can't already solve linear optimization problems. Because linear optimization is a very special case of that. And for many, many cases we know how to solve linear optimization problems. So that's our working assumption, that we can solve linear optimization problems, and we want to lift that up, use the power of that, and see if we can exploit it to solve problems like this. It's helpful in some of the results to assume that my 0, 1 vectors form an independent system, just meaning that subsets of independent sets are independent. For matroids, that's true, but there are many other examples that have that property too. If any of those words mean something to you, then that's nice, but this talk was supposed to be about matroids, so I don't feel like I need to say what those things are all about. But this is a nice, useful property that we take advantage of sometimes. So generally, this is intractable still. And so this is a theorem. I won't do the proof of it, but it's interesting to point it out. Even if W has one row, even if the numbers in W aren't big, in fact they're just 2s and 3s, if little f is given by a comparison oracle, so it only has the power to say, if you give me 2 points in the domain of f, which has a bigger value under little f as a comparison oracle, doesn't give me a value, it gives me which is better. Even if the feasible points form a well-described independent system in the sense I just talked about, you can prove that there's no efficient algorithm to do that, independent of whether p equals np, p doesn't equal np, it doesn't matter. That's a provably exponential problem. Let me just jump ahead and tell you there's a very closely related problem which you can solve in polynomial time. And it's the following. So this is my problem, right? I have one row of W, the entries are 2s and 3s, and little f is only given by a comparison oracle, but I know I can solve linear objective optimization problems over a calligraphic f. I can't give you the optimal solution always to such a problem, but here's what I can do. I can guarantee that I give you a solution, somebody might come in the door right now with a better solution, but it'll only happen once. Okay? Nobody will come in after that person with an even better solution. Somebody might come in later with the same solution, or a solution of the same value as that first person that came in. So there might be lots of people that know many different solutions that are equally better, but nobody will come with a better solution and then have somebody else come with an even better solution. That won't happen. So I can give you an algorithm that will give you a solution like that. So that's not bad. That's like saying, okay, I can write a paper. Paul Seymour will write a better paper, but no one's going to write a better paper than that. So that's not bad to be number 2 in that sense. That's an interesting, result in that you've got these two very closely related problems, one is provably exponential, and the other you can actually deliver, this we call it a one best solution. It's not the best, but it's close to it. Now, keep in mind, little f is given by a comparison oracle, so that person who comes in with a better solution, it might be a lot better. Like Paul Seymour's paper might be a lot better than my paper. But
by comparison oracle, you mean that if you evaluate 2 values?
Yeah, it says which is better. So this person comes in, it's better, but we don't have any measure of how much better. So it's the weakest way you could be given a function that you're trying to optimize. Maybe I'm going to skip this result here. This says something about approximation, that I've got 2 rows of W. You can't even approximate this problem very well. I think I'll just skip the details of that and that. So yeah, let me just skip that. So that's all very negative, and I've spent half the time really talking about negative. So we better have some positive, I think, to leave in a better mood. So here's some positive results. So again, all these results assume that the set of feasible points is well described. For example, the sets that are independent in 2 matroids. That was really our motivating example, but then we realized that it didn't really require matroid properties. So if calligraphic f is well described, if little f is convex, or if you know what quasi-convex is, it could even be that. If W has a fixed number of rows, and now there's some funny words coming up next. Let me say that in a very simple way. If the entries in W are either small or there are a small number of different values in W, that's the assumption. So the matrix W either has an upper bound on the size of the entries. So there's another way to say it is unary encoded. But just think of it as the numbers are small, or there's a small number of different entries. Then there's an efficient algorithm for maximizing. I won't say what the algorithm is. It's just based. It can only be based on solving linear optimization problems because that's what we've assumed when we say it's well described. So you solve a small number of linear optimization problems over f, the right ones, and you can optimize quasi-convex functions like this in polynomial time. If you relax any of these assumptions, then things fall apart. You can say more if, again, calligraphic f is well described, and now f is a norm. So it's not just convex, it's a norm. But now, because I've assumed more about little f, I can maybe assume less about w. And now I can assume w is just an ordinary binary encoded matrix. So that's the normal way you would be given numbers in a binary encoding. Right, so the number 1024, you're not given with 1024 strokes like you live in a cave. You're given it, with 10 bits. So if you assume that little f is a norm, then w can be given to you in a more normal way. Then there's not an algorithm that gives you an optimal solution, but gets you within a constant factor of the optimum in polynomial time. The approximation factor depends on the norm. So it actually depends on the number of rows of capital W. So when I say the norm, there's not one 2 norm, there's many 2 norms. There's a 2 norm on R1 and R2 and R3. So the constant depends on, what norm in that sense. And the last kind of result in this area has to do with minimization. So getting within a constant factor of the minimum. And here you need to assume more that the points are non-negative. We're only really talking about 0, 1 vectors, so that's not a big assumption. If you assume little f is concave, or a generalization of it called ray concave, which just means if I start at the origin and I look into the non-negative orthant, that along any ray going into that orthant, the function is concave. And non-decreasing, and then these harsh assumptions that W should be non-negative, it should have a fixed number of rows, and the numbers in W should either be small or not too many different numbers. Then you can get within a constant factor of the minimum. None of these algorithms are complicated. They all involve solving either a constant number or maybe a linear number of optimization problems and then doing the right thing with the solutions of those problems. So that's the kind of general results that don't just work for matroid intersection, but really work for any well-described calligraphic f. This I already said. Okay, so that's one direction. The other direction, which apparently I talked about on slide 4 once at Carnegie Mellon University, is submodular optimization. So this is a very different topic, but the constraints that I care about are still these matroid constraints. And now we'll see a bit of the matroids actually coming into play here, whereas the other topic really worked for any well-described system, not just matroid intersections. So what's a submodular function? It's simply a function, real-valued function on sets that has this property. So I have a finite ground set again. Here it's called n. And my function should satisfy this property. If I evaluate f on 2 sets x and y, then the sum of f evaluated on those sets is at least as big as the sum of f evaluated on the intersection and the union. I'll mention some examples in a second. But that's the definition of a submodular function. It looks a little bit somehow like convexity, but that's in a way a little misleading. There's another way to think about it, and it's a perfectly equivalent definition with decreasing marginal values. So here the idea is if x is a subset of y, then I think about adding an element to x and to y and seeing what it does. So when I add the element to the smaller set, the marginal value, the improvement, is at least as big as when I add it to the bigger set. That's these things are equivalent. So in a way, you can think of this as kind of a function that has a decreasing marginal value. Throwing something into the bigger set won't give you as much as throwing it into a smaller set, which I think many things in life are that way. Let me just skip that. There's different types of submodular functions. Here's some examples. So let me just jump to this one, which I think is a really good motivating example. Cut functions of a graph. So I have, let's say an undirected graph. And I have a non-negative weight function on the edges. And then I define a function on the vertices of the graph. And the value of a set of vertices is simply the sum of the weights of the edges that leave that set. So that's the cut function of a graph. Some of you might know the max flow min cut theorem of network flows. That's an example of minimizing, or it's an application of minimizing a submodular function. So the cut function, now you think of those weights as capacities on edges. And the function I described, you can think of it on a directed graph now. And it's still the same thing. The value of a set of vertices, the sum of the capacities on the edges that leave that set, not enter but leave. So that's still a submodular function. And minimizing that submodular function is very closely related to finding a maximum flow in a network. And in a way, a lot of the interest on the optimization side in minimizing submodular functions comes from this example. There's an interesting example. It's a little misleading because it's not how I'm going to use matroids when I talk about this topic, but it's an interesting example. So I have two matroids on the same ground set. And I look at this function, the rank function of the first matroid plus the rank on the complement of that set in the second. And that's a submodular function. And minimizing that is equivalent through a certain duality theorem to finding a maximum cardinality set that's independent in the two matroids. So this is it's called Edmonds' matroid intersection theorem. So that's an interesting example, again, of minimizing a certain submodular function. There's some other examples. This one I've spent a lot of time working on. If you have a positive definite matrix, like the covariance matrix of some random variables, and you define a function, so the matrix should be symmetric, and the rows and columns are indexed by the same set. And I define a submodular function on that set, the set of indices, the row-column indices. And the way I evaluate it is I look at the principal submatrix defined by picking a subset of these indices, and I calculate the log determinant of that set. So that's called the entropy or the differential entropy of the random variables that have that covariance matrix. And that's a really interesting submodular function to try to maximize. And there's applications of it, real applications actually in this case, in environmental monitoring. So that's examples of submodular functions that I think are pretty motivating. They're interesting submodular functions, not trivial. Here's the problem we want to look at. So I have some feasible set. I'm going to particularly think about the set where something is feasible if it's independent in a set of k matroids. Not just one, not two, but k of them on the same ground set. My goal now is to maximize some submodular function on those sets. Now, I mentioned before that even linear optimization over 3 matroids is already hard. So now we want to maximize a submodular function over k matroids. That's got to be hard. But my goal is less. I'm not going to be able to exactly optimize. I'm going to try to get within a constant factor of the optimum. And that factor will depend on the number of matroids. So the result I'm going to talk about is that if I need to be independent in k matroids and I want to maximize a submodular function, I can get within essentially this factor of optimal for at least one matroid. So, you know, this generalizes the idea of trying to maximize a linear function over two matroids. We look at k matroids, we ask for less, we just want to get within a constant factor, and we have a much more complicated objective function. So I want to give you an idea how the algorithm works to do this. What's nice is the algorithm is very simple. The analysis is somewhat complicated, but the algorithm is really simple. It's a certain kind of local search. And I mentioned for a single matroid, this local search for minimum weight, maximum weight spanning tree or maximum weight independent set works. And that kind of motivated the idea of trying to use local search for this problem. And you'll see that it works, but you have to do it a little more cleverly. So here's the local search. What I do is I have a solution, a feasible solution, so it should be independent in the k matroids. That's what it means to be feasible here. And these are the kind of moves I allow. I allow myself to take an element of my current set and delete it if, when I delete it, the objective goes up. That's an improvement. I'm trying to maximize. That's one type of move. Then I allow certain kind of exchange moves. So, you know, there's this encoding of, but let me just say it in words. I'm allowed to add an element to my current set. Now, if you think about it, I have k matroids that I have to be independent in. It's maybe intuitive, but it's actually a bit to prove that if you throw an element into an independent set in a matroid, it creates a unique dependency so that if you remove any, there's always a choice of another element to remove that will break that dependency. So it's a natural thing to decide that an exchange move, you add an element, and you might create dependencies, separate dependencies in these k different matroids, so you might have to delete up to k elements to break it. But I'll allow myself to do that if doing that improves the objective. So if adding these elements improves the objective, then I go ahead and do that. That was really bad notation. I don't know where that came from. So, you know, this means adding elements, and why little d is a set, I have no idea, but some latex screw up, I think. Oh, I know what happened. Anyway, it doesn't matter. So do you understand what the local moves are? So you're allowed to delete an element, you can add an element, but then you have to allow yourself to delete k elements. So what we can prove, and I'll sketch the proof of it, and this is where matroids come in a little bit, is this little inequality. That if I have a locally optimal S, locally optimal with respect to these moves, and I have a set C that's independent, so think of that, the way I'm going to use it is that it'll be the optimal set, then I can essentially get a lower bound on the value of S, of this locally optimal solution, and that's what this is, a lower bound. It's not quite the lower bound that I want to prove the approximation result, but that's what we'll use. So I'll kind of sketch the proof of it a little bit. I use a basic matroid property. I just want to give you a hint of how that works so you see where the matroids come in. But it gets used in a very simple way, you'll see. Now, this can't work, actually, the way I've described it. It's not going to find a good solution. And here's an example where you see it doesn't. So think about directed graphs again, where I have weights on the edges. The weights on these blue edges are 1. The weights on these red edges are some big number, m. And I think about no matroid constraints. Then I think about the local search. The local search is just moving a single element now if there's no matroid constraints. And think about the value of this solution, just these vertices. The value of it is 4. But if I move a single vertex, so it's not pairwise exchange, moving a single vertex out of the set, then I lose something. And if I move a red vertex into the set, I gain what do I do? Directed. Oh, no, yeah, if I move this red element in, I lose the 1, but I don't gain the m. Both of these are on this side now, so nothing is leaving from this pair. So if I move a blue over or a red over, nothing is crossing anymore, so I don't gain anything, I only lose the 1. But that's a terrible solution. What I should have is this solution of all the red vertices and have 4m crossing. So the local search that I described can't work. So we've got to do something about it. And the observation is that in the bad example, this example, the optimal solution is actually completely disjoint from this locally optimal solution that I showed you. So why don't we try to remedy that for this example and see if it actually gives us something in general. So, oh, this keeps going the wrong way. So here's what I'm going to do. I'm going to run the local search just like I described. Then I'm going to run it again on the complementary set from the locally optimal solution. So I take the locally optimal solution, I pull it out. Now I run local search again on what remains. And then I'm going to take the 2 locally optimal solutions and take the better of them. And the better of them actually gives you a constant, within a constant factor of the optimum. So here's how the proof works. So again, I'm going to assume this lemma here and use the lemma. We still have to prove the lemma, but this is how the proof goes. So let's let C be the optimal solution. So it's a little picture of it over there. S is the locally optimal solution. It's some other set that might intersect C. I define D to be the complement of, well, not the complement, it's C minus S. So, you know, C is all of this. I take away the part of S that's in C, and so that's D is what remains. Then I run the local search over the complement of S. I get some other set T, which might intersect this picture like that. So S and T are both locally optimal, so I use the lemma twice. Then I add these 2 inequalities, but I throw some stuff away on the right side. So what do I throw away? I throw away that, but this is non-negative. I throw it away. And then I turn that K into a 1. I'm just decreasing the right side, so I can do that. And I get this inequality. Then what do? I look at this and I apply submodularity to these 2 sets. So S union C and T union D. When I take the union of them, I actually get that. When I take the intersection, I get that. Then I apply submodularity again to these 2 sets. And I throw some stuff away. It's believable. You can check it later. So in the end, I get this. And that's all I need because, you know, I divide both sides by k plus 1. I've got the sum of 2 things, at least the value of the optimum divided by k plus 1. So at least the better of them must give me a factor of half of that 1 over k plus 1.
Are you assuming that f of mt is 0? Or?
That f is non-negative, just non-negativity. Yeah. Yeah, and all these approximation results, when you're maximizing, you need non-negativity, or it doesn't make sense to talk about a constant factor of like that. So you can shift things by a constant if you want. Oh, I'm going the wrong way. Okay, so that's something, but you can do better. So I won't do the proof of this, but the same thing you can actually improve on. So if I have k matroid constraints, I should actually do what I just said, k plus 1 times. So I find a locally optimal solution, take it out. What remains, find a locally optimal solution, take it out. Do that k plus 1 times, and then take the best of those solutions, and that you can prove gets you within this factor. And that has a more complicated use of submodularity, but it's still line by line, it's elementary, it's just tedious. So that's good. Let me just say a little bit about how the proof works. So this is only interesting if you know something about matroid intersection algorithmics. Does anybody know the matroid intersection, maximum weight matroid intersection algorithm? You do? Okay, can you tell us how it works? No, I'm kidding. I do this to people all the time. It's one of my favorite jokes. So you build something called an exchange graph. So it's just like it's a bipartite graph where the elements on the left are elements that are in your current independent set, and the elements on the right are ones that are not in the current independent set. And then you think about, you've got this independent set on the left, here's something that's not in the independent set, and you think about, if I throw it into this set, it creates a unique minimal dependency as a subset of that set, and I put edges pointing from the right to the left, indicating which elements are in that unique minimal dependency. Then I do the same thing thinking about the second matroid. So there's this k matroids, but I think about that, and I could put edges in the other direction. So for two matroids, I can kind of get this dependency graph, and I use that graph in a certain way, this exchange graph. It's actually, if you want to read about this, it's a bit of a hunting experiment, but Lex Scriver has this 1,500-page book on combinatorial optimization. There's 3 huge yellow volumes, and it's described really well in there if you want to find short, concise proof of this, this kind of device here that's used. So anyway, you use the same combinatorial device that's associated with the algorithms for matroid intersection with linear objectives, and you play with that exchange graph, and you can get what you want. So that's really all I think I should say about it now. So there's an unfortunate detail about all this. That algorithm doesn't run in polynomial time, that local search. So it gets you within that factor, but it might take exponential time. So the way you make it polynomial time is you sacrifice a little bit. So what you do is you do those exchanges, but you require an improvement of at least so much. And there's an epsilon here. And same thing here. You stop if you only get a little improvement. And if you do that, you can prove the same lemma, but with a factor of 1 plus epsilon here. And that gets you the result that I mentioned. Let me just quickly page back to what the result is. Maybe it's gone, but maybe it never was there. So it gets you that, but then there's an epsilon in there, an additive epsilon in the denominator. Maybe I never actually had a slide that had what the result is. So yeah, unfortunately, you can't quite get these, in polynomial time without that epsilon. So we have improvements on this. You can make the local search more powerful by adding not one element at a time, but p elements, and dropping k times p elements, where this p depends on the epsilon. And if you do that, you can get within this really nice factor. As long as k is at least 2, you can get within almost 1 over k of the optimal with k matroids. And that's actually an improvement on an old result of Fisher, Nemhauser, Molsey. Maybe that 30 is 35 now. But they proved 1 over k plus 1. So this is essentially 1 over k now. And skip that green. Yeah, so I just want to talk about this one last thing. I have 5 minutes just to tell you what the result is. This is something I did with Maxime and Jan Vondrak when we were all 3 at IBM. And then I went to Michigan, and Maxime went to Warwick, but he didn't like it there. He wanted to go back to New York, so now he's at Yahoo Research. But it's an interesting thing. When we worked on this, we were all at IBM, which you would think is working on very applied problems. But maybe that's why we left. But anyway, let me just briefly tell you what this problem is, since we're only up to slide 2, by the way. Now we've jumped ahead to 5. So let me see if there's some slide that really... let me just tell you what the problem is. So this is the matroid parity problem. So it's an old problem. It's talked about in Lawler's combinatorial optimization book from the 70s with some mistakes, but here's the general idea. You have a matroid on a ground set, and elements are paired together. So for every element, there is a buddy. And what you want to do is find a largest independent set, but there's this side condition. If you pick an element, you have to pick its buddy. So it's a pretty simply described problem. The nice thing is it includes matroid intersection and matching in non-bipartite graphs. So I do have a slide that explains those two things. If I want to model matroid intersection as matroid parity, what I do is I take the direct sum of M1 and M2, duplicating the ground set. So M1 and M2 in matroid intersection define in the same ground set. What I do is I duplicate the ground set and I define them separately. And then I pair up elements. So every pair of duplicate elements, I just pair up. So if I pick one here, I've got to pick its buddy over there. So that's an easy way to model matroid intersection as matroid parity.
Excuse me, what is the problem?
Find the largest independent set, but the side condition, if you pick an element, you have to pick its buddy. So they're not weights, it's largest in cardinality sense. There's also, you can model matching as matroid parity. Now I said bipartite matching is an example of matroid intersection, but there's also matching in non-bipartite graphs. That's a more complicated matter, and that's not modeled by matroid intersection, but it is modeled by matroid parity. So this happens to be a bipartite graph, but it's just illustrative of the modeling technique. So I want to find a largest matching in this graph. I want to model that as matroid parity. What I do is I take each edge and I split it like that. And now I say that I want to pick a set of edges that's doesn't touch any black vertex more than once. That's the first condition. That's a matroid after I did the splitting. So think about all these edges that touch that black vertex. I'm not allowed to pick more than one. The other endpoint isn't black. So it's a direct sum of these uniform matroids where I look at the ground sets as the sets of edges that touch black vertices. But now I have this parity condition. If I pick this half edge, I have to pick that half edge. So elements are paired up with their buddies in a natural way induced by the splitting. And then I'm really, the feasible sets now really are matchings in any graph if I do this. So it's a nice way to model, to bring together matroid intersection and matroid parity. And Lawler conjectured back in the 70s that you could do this in polynomial time. And he had some partial results, which unfortunately were partially wrong. And Lovász actually proved, where is it? Lovász proved that you can't do that in polynomial time in the oracle model of matroids. So if the matroid is given by an oracle, you cannot do it in polynomial time. But if the matroid is given by a matrix with linear independence, you can do it in polynomial time. It's a really kind of beautiful contrast. And what's a bit interesting, I'll just go 2 minutes over, is that most matroids are linear, not in a mathematical sense. Most matroids are not coming from matrices. But if you look at all the examples, they tend to come from matrices. And there's actually a quote in this 1,500-page book of Schrijver that says most of the matroids we meet in everyday life are linear. It depends what your everyday life is, whether you're meeting very many matroids. But actually, this joke here is that something stronger is true. Most matroids that you meet in everyday life come from graphs, really. And graphic matroids are linear. So the matroid that comes from a graph does also come from a matrix of a certain type. So you could say, well, look, if we're really interested in matroid parity, and most matroids really come from matrices, most matroids that we care about, maybe that's the end of the story, and we shouldn't worry about solving the matroid parity problem in the Oracle model. But, you know, why not? So let's let him go away. I'll skip all this. I mean, the algorithms were very complicated of Lovaas. The original one was n to the 17th, which is not very useful. But it's been improved quite a lot, n cubed times the rank, essentially n to the 4th. So I'm going to skip all this and just tell you what we have. So for matroid parity problem, in the Oracle model, so meaning that I don't have a matrix that defines the matroid, I just have a black box which tells me whether a set is independent or not, we can give, even though it's provably exponential, we can give a polynomial time approximation scheme, meaning that for any fixed epsilon, we can get within 1 plus epsilon of the optimal solution. Yeah, I'll just say it like that. So that's when there are two matroids. Generally, we can get within, for k matroids, there's something called k parity. You can imagine what it is. You have k tuples instead of pairs, and we can get within this constant factor. But our factor is, you know, essentially 1 with an epsilon when k equals 2 for the problem I really described. So that's really shocking to most people who work in matroid algorithmics, that the view is usually if you can make an algorithm for the linear case, the nice thing about matroids is somehow it's going to work in the Oracle model. And here the Oracle model is, you know, provably exponential, but you can get within, you know, epsilon of the optimal solution, even in the Oracle model. So I just tell you what the algorithm is. It's local search. So the local moves are pretty simple. I have a set that's independent. The way it's written here is maybe, yeah, this is for parity. So I have two sets, and I say a local move means take S minus 1 pairs that are in A. So there are pairs of elements that are, you know, paired together in the sense I talked about before. And I have S pairs within B, and I swap them like that. So I move whole pairs. So in a way, it's the simplest local search that you could think of. But you should only do a swap like this if you keep independence. And what you can show is that for any positive epsilon, if you do local moves of this size, which is pretty big, local moves, you can get within 1 minus epsilon of the optimum. So I'm not going to go through the details of it, but that's the algorithm. It's a simple algorithm. It's quite a complicated analysis. It's much more complicated than that other algorithm that I sketched out how it goes. But the algorithm is pretty simple. It's big local moves, but this is what does it. What's interesting, again, it's a contrast from what goes on in the known case of linear objective and matroid intersection, is that polyhedral results, linear programming-based methods, don't work here. So we can give examples, which are on the next 7 slides, where if you look at natural linear programs that are relaxations of this, the gap between the optimal solution and the maximum parity size is huge. So you're not going to get a good algorithm based on rounding a linear programming solution. That's what you would hope for if you're trying to find an approximation algorithm based on linear programming. And that can't work here. You really have to use local search to get something out of this problem. So that's all I'll say. I'm 5 minutes over, so I think it's good to stop.
Thank you.